next hour or so, 45 minutes, we're going to be talking about waves. I'm going to spend the first 20 minutes on some introductory material, and then Callum is going to build on that and talk about large waves and how they develop. So this is famous print from a woodcut, the large wave off Canoecopia. Waves are important things for paddling, and the first thing we want to understand about a wave is it's a movement that transports energy and momentum from one place to another with just small oscillations of the medium and not a lot of movement. So everybody's probably seen the wave in a stadium, so I want us all here to do the wave, yes? So we'll go down this side and then back up the other, yes? Are you with me? You ready? On three. 1, 2, 3. There we go. Yeah? So there's a movement that propagated around the room, carried momentum, carried energy, but you physically were in the same place as when you started, yes? And that's what waves in the water are like. They're small oscillations. In deep water, those particles are traveling in circles, but there's a large motion of the wave resulting from a very small oscillation of the medium. So I need to define a few terms for the rest of the talk. So when we talk about wave height, a lot of times when people talk about the height of a wave, they'll talk about an amplitude, which is the middle point to the top or to the bottom. But when we're talking about waves on the ocean, the height is the place from the trough to the crest. The amplitude is 1/2 of that. The other length we need to define is wavelength. Often we use the Greek letter lambda for that. If you take a picture of a wave, the wavelength is the distance in space over which a wave repeats. So it is the peak to the peak, or the trough to a trough, or an upward crossing to the next upward crossing, but it's the length in space over which a wave repeats. Periodic waves, they repeat in space and they repeat in time. So we can define a quantity called the period, which is the unit of time over which the wave repeats. So if the wave comes up and you start your stopwatch and it goes down and it comes back up again, you stop your stopwatch, that is the period. The frequency of a wave, which you talked about, is just 1 over the period. There's not going to be a lot of equations in this talk, but this is an important equation for waves. It says that the wavelength is equal to the speed of the wave times the period. Now, let me see if I can convince you, even if you haven't seen this formula before, this is a formula you all know, because many of you maybe on average traveled 120 miles to get here. If you're driving on the highway at 60 miles an hour and you travel for 2 hours, how far do you go? 120 miles, yes? Speed times time is distance. That c is the speed of the wave. T is 1 period, and if you watch that wave, 1 period later, it has traveled exactly 1 wavelength. Distance is speed times time. It's the same equation you used to figure out when you had to leave to get here on time today. So that would be important to us because waves, as they come in and the depth gets shallow, those waves are going to slow down. And as they slow down, the speed gets smaller, and that means the wavelength gets smaller. If the right-hand side of this gets smaller, the left-hand side gets smaller. The period of wave can't change. And one way to imagine that, if 2 people are shaking hands, one has a really long arm, one has a really short arm. Their arms are different lengths, but as they shake hands, their hands are going up and down at the same rate. That doesn't change. So the period of a wave doesn't change. But as it slows down, they have to bunch together. Those wavelengths have to get smaller. So that's the speed of a wave. The speed of the wave also, it does depend on wavelength and depth. So there are 2 regimes that are important to think about waves in. In deep water, waves are dispersive, and that means that the speed of a wave depends on its wavelength. So a really long wavelength wave travels fast. Something that has a smaller wavelength travels more slowly. In shallow water, the speed no longer depends on the wavelength, now it depends on the depth. And in really shallow water, the wave travels slow, and as the water is deeper, it travels fast. Last set of equations I'm going to give you, and then no more equations, but it's good to have some rules of thumb for how fast a wave is. So, how many people here are kayakers? Yes? And so what would be a typical speed that you would paddle at?
4 to 5
3 knots, maybe, yes? If you really were to sprint, to try to catch a wave, your top speed might be around 6 knots. Yes, that's not something you're going to sustain over a day, but that's like your top sprinting speed. In deep water, the speed of a wave goes like the square root of the wavelength. And it turns out that in deep water, your speed is 6 knots, and then you take the wavelength and divide it by 6 meters. 6 meters is very close to the length of a sea kayak. So if you want to estimate the speed of a wave out in deep water, you measure the length of that in terms of your boat, you take the square root of that and you multiply by 6 knots, and that is the speed of the wave. In shallow water, it no longer depends on the wavelength. So what you'll do, take that 6 knots and you'll multiply it by the square root of the depth. So waves travel at these speeds. They're dispersive in deep water. They slow down in shallow water. They mostly travel in straight lines, but there are a few important cases where they don't, and it's important to understand those. Waves can reflect, and then there's 2 ways they can bend. One of them is called refraction, and the other is called diffraction. So waves, when they come in, and say we're looking down from above and they hit a cliff, when they come in, they bounce off at the same angle symmetrically. We would say the angle of incidence is equal to the angle of reflection, and so if the waves would be coming in more steeply, they are reflected off more steeply. That's for a cliff. If you go to a beach, however, no matter where you go in the world, when you watch the waves coming into the beach, those wave fronts are always parallel to the beach. They're almost always parallel. Why is that? There has to be a reason, right? You go to one side of the island, they're coming in parallel. You go to the other side, they're coming in parallel. The reason for that is refraction. So you remember we said that the speed of a wave depends on the depth when the water gets shallow. As a wave goes from deep water to shallow water, it slows down. And so here you see a wave coming in from the deep water, and it goes through a series of steps. One step it slows down, and so this part lags behind. The next step it lags farther. And so if you look at that wave, over time it's bending more and more, and those wave fronts are becoming, and here I've just done 2 steps, but if you imagine many, many steps, over time those wave fronts are coming in parallel to the beach. That is called refraction. And if you study how the waves refract, if you look at how those wave fronts are becoming parallel to the beach, you can form a mental image for what's going on with the depth underneath the water just by studying how much they bend. The final way that waves will bend is called diffraction. And diffraction is going to let waves bend into the shadow region. And to figure out how that works, we'll use Huygens principle. So this is a wave coming in, and Huygens principle says each point on the wave you consider as a source of new waves, and then to get the wave later, you just draw in a line that's the envelope that's tangent to those curves. So here's a little break wall, and here's a wave that comes in. So here's the wave, each point's a source of a new wave. I draw in a wave tangent to that, and the wave propagates in. This is diffraction, and through diffraction, waves will bend around into the shadow region. So all of these things are important for landing, for launching, for where to paddle. So because of refraction, because those wave fronts become parallel to the beach, if you've got a bay here, those waves get spread out, and the energy and the amplitude of those waves gets reduced. So these are relatively easier places to land, less good places to look for surf. Headlands, the sticky outy parts, refraction concentrates the waves there. So the amplitudes are going to be higher, right? The surf zone is going to be more challenging. Harbors like this, the wave action will be reduced, but there will be some because the waves can diffract into that shadow region, into the harbor. And finally, places where you have cliffs, those waves will come in and they will reflect off. And so you'll get an incident wave and a reflected wave. And so now we need to understand when you've got 2 waves crossing the same space, how do they interact? So we need to talk about combining waves. But combining waves is really simple, and here are some beautiful pictures from David Sanford of waves on Lake Erie. And we're going to talk about how to combine waves to get these kinds of shapes. And it's really simple. If you've got here's a red wave and a blue wave that happen to be passing each other. And to know what's going to happen, all you do is you take the red wave and you add it to the blue wave. The resulting wave will be purple. So look at this. So here's the red wave. If I add that to the blue wave, I get the purple wave. Take the red wave, add it to the blue wave, I get the purple wave. Here, that red part is negative, so I have to subtract it from the blue, and I get the purple. Yes? That's called the principle of superposition. It just says I add up the heights of the waves, and the resulting wave is just the sum of those heights. So there are two extremely different cases that give me really different results when I do that. So here, the red and the blue wave are lined up. This is called constructive interference. The peaks get higher, and the troughs get deeper. The opposite of that would be where the peaks of one wave are aligned with the troughs of another. Now, they just cancel each other out. So remember our reflected wave, where we had an incident wave and a reflected wave? Those can give you clepata. So here's a picture of some clepatas out on the west coast. This is a picture Alec Boyd-Peshkin shot of that Sharon there, of some clepatas down near Montrose in Chicago. So here is an incident wave coming in. There's the reflected wave. This is a snapshot in time. And if you look at now, the peaks are lined up. Yes, the troughs are lined up. So these will add up to give me this huge wave. Yes? But this wave is moving to the right, and the blue wave is moving to the left. And so as that happens, at some point, now the peaks line up with the troughs, and those waves cancel each other out. So these reflected waves, they give you a wave here that just goes up and down like this, bouncing up and down. And that wave will be twice as big as the original wave. That's clepatus. And if the reflection isn't exactly, if it comes in at an angle, you can get waves like that that'll actually move parallel to the shoreline. So that's one important use of the principle of superposition. The other one is, how many people here remember sines and cosines from grade school? Yes, you remember those shapes? Well, we always use sines and cosines, and I've used them here to make pictures of waves. But next time you go out on the lake when the waves are big enough to be interesting, take a look at them. When a wave is big enough to be interesting on the lake, it is not well described by a sine or a cosine. It has a different shape. And we can use the principle of superposition to figure out why. How many people here play a stringed instrument or played one in the past? A number of you. You know when you pluck a string, you excite not just the fundamental mode, but the harmonics, yes? And when waves get big, the same thing happens. You excite not just the fundamental mode, but the harmonic. So here's the fundamental mode. Here is a harmonic where this wavelength is half that. This one is a third. And here is an example of what happens when the waves get big. Here is a cosine wave there in blue, but it's not just a cosine. You get its first and second and third harmonics. And if you look here, all of those things add together and they give you a peak that is much sharper and much pointier than a sine or a cosine. And here in the troughs, there's a cancellation and the troughs become flatter. This wave is known as a Stokes wave after the physicist who first worked that out. But what this is telling us is that in deep water, when the waves get tall, they're not like sines and cosines. They get pointier like this. And here in green in the background is the wave where I didn't include the point. But the actual physical wave is sharper and pointier and flatter in the peaks. And the waves will grow like that in deep water until the height, the distance from the trough to the peak, is about 1/7 of the wavelength. And then the waves can't support each other and they'll start to fall apart and you'll get white caps. Now I've exaggerated the scale by 2.5. So this actual wave here is much steeper than a physical wave would be, but I've exaggerated so you can see it. But that's the criteria in deep water. We can do a similar analysis in shallow water, and the result just becomes more exaggerated. In shallow water, those bigger waves, we call them canoidal waves. So there's Stokes waves in deep water, canoidal waves in shallow water, and it's more exaggerated. Those troughs become flatter, and then you get those sharp peaks separated by larger and larger flat troughs. And if you look at pictures of waves, this is a picture of a canoidal wave off the coast of France. There's actually canoidal waves coming in from two separate directions, and you can see there's some superposition going on but you can see this quick up and down separated by those long flat troughs. And this is what, next time you're out, look at those waves. When they're big enough to be interesting, they're not sines and cosines. As the waves come into the beach, they shoal and they break. So here's a wave coming into the beach. So this isn't a cartoon. This is an actual calculation, but it's scaled up so that you can see it. So the vertical scale is increased by 3 and the wave height by 5. As the waves come in, they slow down. 3 things happen. They come in, it gets shallower, they slow down. As they slow down, they bunch together. But until they break, energy has to be conserved. And for energy to be conserved as they slow down, the only way to conserve energy is for them to grow in height. So 3 things happen as waves shoal, as they enter shallow water. They bunch together, they slow down, and they grow in height. And this is how that happens, right there. And then eventually, they'll get so tall that they'll break. And this is a wave, this is a picture taken by Scott Faraday. That's my sea kayak there. And there's like 10 feet of an 18-foot sea kayak over a wave, which is just in the process of breaking. And so in deep water, they break for a height of about 1/7 of the wavelength. In shallow water, they break when the depth is about 1.8 times the height. This I find kind of interesting. You will see this number reported differently in the literature. You'll see it reported as 2. You'll see it reported as 1.4. It is a remarkably difficult number to get a handle on. You can ask Callum more about that. Callum he is one of the world's experts on this. Has done these measurements, his PhD thesis on these kinds of things. My personal judgment is maybe the 1.8, something closer to 1.8 than 1.4 would be better. So as those waves break, whether they're dumping or whether they're spilling, depends on how quickly it becomes shallow. If it becomes shallow abruptly, they're going to dump. If it becomes shallow more slowly, they'll be spilling. So if you're launching from a beach and conditions are building, particularly if that beach is steep, you might want to think hard about where your takeoff spot is, where your takeout place is, because by the time you get back to that beach, you may have dumping surf that's difficult to navigate. So all of these things hopefully make you better in the surf zone. One last thing I want to explain about the surf zone. Although it's subtle, it's really important. It's about wave sets and about 2 different speeds that a wave has. There's a speed called the phase velocity and a speed called the group velocity. So if you've ever studied surf or the waves when they're coming in, they come in sets. So the waves go up and down, and then not so much, and then they go up and down again, and then not so much. They come in sets. Why do they come? But in understanding that they come in sets, we'll tell you when to take off so that you get a nice ride. Why do they come in sets? Well, storms create waves. And you will remember that the longer a wave is, the faster it travels. Yeah? So when a storm creates waves, you've got all kinds of different crazy waves, the different wavelengths added together, and you've got a confused, choppy sea. But if you go far away from the storm, the longer waves are faster, and they win the race. They run out ahead of the slower waves. And so the waves become really well sorted. So out here, you've got really long wavelength waves. But actually, you have a combination of waves that are close but not exactly the same. Because you'll have waves here from the front of the storm, and then you'll have waves of a slightly longer wavelength that came from the back of the storm that just caught up. Yes? So here is 2 waves like that. A slightly longer wave from the back of the storm and a shorter wave from the front of the storm. And because this is a longer wavelength, it's slightly faster. And because it's a little bigger, the place where constructive and destructive interference happens, it changes. Yeah? So here's destructive interference, then it's constructive, now it's destructive. You see the wave sets? There's 2 waves here. There's a fast wave wiggling through, and then look at this, there's a slower wave. Do you see that? That's also like a sine or a cosine shape there, right? Yes? So there's 2 waves. Those 2 waves travel at different speeds. So I want you to watch this peak. So This is going to move to these. I'm going to start this moving. This is going to move to the right. That's going to move to the right. This is a little faster, yes? So watch that peak. So it was one of the first waves in the peak, but now it's the top wave in the peak, yes? And now it's getting smaller. So the little faster wave is moving through the bigger wave. So this is important for a number of reasons. If you're out here in a surf break and you're waiting for a big wave to come to you that you want to surf in, surfers know to be patient. Don't take the waves that look good. Wait and take the ones that come behind it. Because by the time those waves get to you, they're going to be the big waves. Last point. Another way, you come back to your beach with dumping surf because it was too steep. You're trying to get through the surf zone without getting wiped out. You might start entering the surf zone here, yes? But eventually, if you start here, you'll get moved back into the big part of the set. So if you're trying to come in where the waves are small, you need to let a few waves pass you by so that you don't get back into the big part of the set. And hopefully this information will help you guys to have more fun in the surf zone. Thank you for your time and attention. And then Callum's got quite a lot, so we'll switch up.
Thank you very much, Greg. Whoops. So we both get a wee bit of wave art into our presentation. I found a website. I had a series of fantastic art pictures. These are paintings, and they were exceptional to me because they embodied this kind of scary kind of melee that is the sea in a big storm. I want to talk about something related but slightly different to Greg. I want to talk a little bit more about how waves form in the ocean. But before I do that, I want to talk a little bit about the different kinds of waves that you will find in the ocean. I want to concentrate on wind waves. These are waves generated and growing bigger because of the effect of wind. But there are other types of waves. So we have a seiche, which is produced by change in atmospheric pressure or storm. We have a seismic sea wave, a tsunami, generated by faulting of the seafloor, or because of an underwater landslide, plate activity. And then of course we've got the tides. I'm going to concentrate on wind waves. Now wind waves are those that have been initiated, and are building up because of the action of wind. And those start off with tiny little capillary waves. If you imagine a flat water surface with wind blowing across it, it's those ripples generated by the interaction of the wind on the surface that are these capillary waves. And these capillary waves are so named because they're dominated by surface tension. Then we have ultragravity waves, short wind waves, ordinary wind waves, infragravity waves, great long wavelength waves, and then of course the effect of storms and earthquakes, and then finally the tides. In the absence of wind, there is a phenomenon called the doldrums, and these occur in the intertropical convergence zones, at the boundaries between these large recirculation zones in the Earth's atmosphere. And with no wind, the water surface can become extremely flat. When we do have a wind, and it's a very unnatural situation to have no wind and then, a well-conditioned wind, but these images were taken in a lab with a wind tunnel retrofitted on top of a wave channel, in which the free surface of the water is then available to be worked upon by a wind that we know exactly the velocity and the characteristics of. And then when this light wind blows across the water, it forms what's known as cat's paws in some circles, little dabbles. And that's just the initiation of a change in the surface to become rippled from a flat surface. Now, as wind moves across a flat water surface, there is an interaction between the wind and the surface. It generates a boundary layer, and that will result in pressure variations, small pressure variations on the surface, which initiates these ripples. These ripples, as I mentioned, are capillary waves, and they're dominated or held, sustained by surface tension. If that light wind above a certain threshold continues, then these ripples become longer and longer in wavelength. And I want to talk next about how that happens. As I mentioned, the restoring force that allows these tiny little waves to propagate across a water surface is surface tension. And that is rather like what happens when you blow across the water, or blow across your coffee or your tea. You know, the action of your breath blowing across the surface picks up or roughens the water surface and allows it to be worked upon even more by the airflow that follows. So surface tension is a characteristic of liquids, where the molecules in the liquids are attracted to each other. And when you come to a free surface, the effect is that the molecules at the surface are retained by the body of the fluid more than outside. And so it forms something like a skin, an elastic skin. And you can see the skin when you see these little water boatmen, insects that land on the surface of a flat pond. You can see how the surface tension kind of sticks the water to the ends of their pads. So you can visualize in your mind that it's got kind of a skin on it, and that skin is kind of elastic, and it's that which sustains the motion of these small capillary waves. Real seas are larger scale motions, and these form under the effect of sustained winds. And for those, the restoring force is gravity. Once the waves get above a certain size, then you're actually lifting and dropping a certain mass of water. Yeah? And so the restoring force is the force of gravity pulling that water back in place. The boundary between capillary waves and gravity waves comes at about 1.7 centimeters, so even less than an inch. They're dominated by surface tension, that sticky skin effect that you get in water. Above that, gravity becomes much more significant. Once the water surface is disturbed, then things really begin to pick up. You still have a wind or you have an airflow above the water, but now the surface of the water is rippled, and that rippled surface then interacts with the air that's flowing across it. And this is a kind of cartoon depiction of what's happening here. You have, in some cases, you have differences in pressure which are exacerbated by the change in the surface produced by the surface tension ripples. So these wind waves are now moving into the regime of gravity waves, but they evolved from capillary waves. This illustration shows how these ripples are increasing in amplitude, and what you have is an effect where, if you imagine that surface there, it's almost like a winged surface, a curved surface, and as the air moves across it, it produces a low pressure region which sucks the peak up, and on the other side you end up with a corresponding high pressure region which pushes the trough down. This is a little bit of a simplification, but this phenomenon has been studied in a lab environment under well controlled conditions. And as the wind continues to work on the surface of the waves, this effect carries on and the amplitude of the waves will increase. Now, at this point, there is a phenomenon that is quite complex. Now, I don't think it's fully understood, but it's related to the non-linearity. Greg mentioned how realistic waves in the ocean are not sinusoids. The ripples, the little capillary ripples, are quite close to being sinusoidal, but once the waves develop in a realistic sense, they are no longer sinusoidal. They have harmonics, they have high amplitudes, and when non-linear waves interact with each other, they don't just pass by. So if you have waves crossing each other or catching up with each other, what happens is that there's a transfer of energy from shorter wavelengths to longer wavelengths, and that's why after a storm, what's left, the relic of the storm, are these big swells, because all the energy from these short wavelengths, from the capillary waves through the gravity waves and onwards, are all fed downwards to this swell. So there's these three phenomena: the wind working on the surface of the water, the wind working on the rippled surface of the water to amplify and generate larger waves, and then you have this transfer of energy to longer and longer wavelengths. How this evolves over time, or how the waves end up, is influenced by 5 factors. Obviously, the size of the waves is going to be influenced primarily by the wind speed. The higher the wind speed, the bigger the waves you're going to expect. And of course, it's also influenced by the distance of uninterrupted water over which these waves are evolving. I started kayaking in the Great Lakes and Lake Superior in Michigan, and you become used to the kind of waves that you get there. And they're really quite different from ocean waves, where the fetch is much larger and potential for much higher winds is greater. Even the width of the area, so I mean, if you're in an ocean which has an extent of hundreds or thousands of miles, this will also influence the size of the seas that you're likely to encounter. And of course, the wind duration, how long the wind blows for, is going to have an influence on how big the sea is going to get, and then the water depth as well. So once the wind has been acting on the sea for quite a long time, generates big seas, there's a lot of different wavelengths present in this. I mean, if you've been out in chaotic conditions, you can tell that there are certain different wavelengths present there. And Greg mentioned just in passing that you can characterize a certain arbitrary wave function by breaking it down into its fundamental sines and cosines. This is called Fourier analysis, and it's used in almost all areas of physics, and it serves us very well here. A complicated pattern of peaks and troughs can be represented by a relatively small sum of sines and cosines. And you'll be familiar with this phenomenon. One example I can give is the album by Pink Floyd, with this prism. It has white light going into it, and it's dispersed out into its various colours. That white light is spread into its spectrum, yeah? And that's kind of what you're doing here. You're taking a given pattern of sea height across an area, and you break it up into its fundamental constituents. This is a perfect way, or it's a very useful method to characterize sea states. And you wonder, why would you want to? Well, these are used for predictive purposes. If you know how high the wind is and what the conditions under which that wind is blowing, you can then, from previously measured spectra, you can calculate or you can estimate what the height of the waves or what the typical maximum wave height is going to be for a given area. And this is used for shipping warnings and for a variety of other things, including for like North Sea oil, for recreational boating. Got 2 spectra here, and these feature a lot in hydraulic research. There's a Pearson-Moskowitz spectrum, and this was measured from boats. Boats were sent out into the ocean, and they had instrumentation which they hung off, and under certain conditions they measured the wave spectra. So they're measuring every fraction of a second, taking all that information, collating it, and then doing a Fourier analysis on it and breaking it up into its constituent sines and cosines. So what you've got here is frequency across the bottom. 0.06, so the longer wavelengths, that's the long swell, is down at this end. Yeah. The higher frequency, the shorter, choppier waves, are up this end. And in a crazy sea state like this, you would expect there to be a range of wavelengths. In fact, the pattern for a given maximum wind speed is rather similar as the wind speed increases or decreases. It's called self-similarity. And because of that, it means that you can plug this information into a formula very conveniently and then use that to calculate or estimate wave heights. This was done in the 1960s, the Pearson-Moskowitz spectrum, but by taking that data and plugging it into a formula, they found out that there was an error, or there was something not quite right with it, because it predicted at some point that the speed of the waves that could be generated by this spectrum was faster than the prevailing wind, so there was something unphysical about it. A number of years later, they went back out to sea with more boats, more instrumentation, and they measured this joint swap spectrum. And this is a joint North Sea wave something. It's a multinational effort, basically, to come up with the best quality sea spectra data that we could. And this John swap spectrum tends to be the one that is used most frequently for predictive purposes. My interest or my involvement with stuff like this in the past hasn't been for predictive stuff, it's been for modelling waves and wave type situations in the lab, because this spectrum measured in the real world is then taken and plugged into instruments to recreate these kind of conditions in a more controlled environment in a lab. I'm not sure why I inserted these three. I think they were just examples of the kind of high sea conditions that you get both in Lake Michigan, Lake Superior, and then of course the Atlantic Ocean. Clearly the Atlantic Ocean generates bigger waves than the inland lakes because the fetch is bigger, the maximum wind speed is going to be much higher as well. This is a German surfer who apparently surfed a 100-foot breaker just off the coast of Portugal. Then I'm going to talk a little bit more about lab stuff, but I just wanted to mention this. We mentioned fetch and wind speed, and the highest waves here are the ones depicted in red. So we've got like red here between 5 and 6 meters average wave height. And these are all around here in the South Atlantic, where basically you've got an uninterrupted stretch of water that goes on infinitely, because it stretches all the way around the world. And in that region of the world you get extremely high sustained winds, so of course the biggest waves are going to be down there. And that's of course documented widely in history with boats making journeys down. And the other interesting thing about this is that these images are taken from space using satellites. They use radar capability. They fire radar pulses down and measure the scatter of the signal coming back. If you've got a flat sea, that pulse is going to be reflected back more or less as it is. If you have a crazy sea state with a lot of different wave amplitudes, that signal coming back is going to be spread out over time and also spread out over space. And that's the means by which they map out wave height, and then from that they then imply what the wind speed is. So the wind speed was not measured, the wave height was, and the wind speed was implied from it. Greg mentioned a bit about wave dispersion, and I just mentioned briefly that the storm can be many, many miles away. But the first thing to reach you is going to be the long wavelengths. These long wavelengths move much faster than the short wavelengths. You can imagine, in the bath, you can dip your finger in and it makes a little set of ripples and they propagate out. And with the light above, you can see these ripples moving across. They're moving quite slowly. I mean, you could time them across the bath if you wanted to. But these big swells are moving extremely quickly. That big wave that you saw with the surfer on it, a 100-foot wave, as it approaches the shore, it'll be traveling faster than 40 miles an hour. And you imagine the tides. I mean, the tides are circumnavigating the globe at phenomenal speed. The longer wavelengths travel much, much faster than short ones. And this is an important concept to understand for what I'm going to show next. So the longer the wave speed, the longer the wavelength, the faster the wave speed. I've got two movies here. These were taken, this one was taken in the early 1980s, and it was related to a wave power project that was started by Professor Stephen Salter. He had the idea that by putting devices into the water, into the waves, that you could extract energy from them. And Salter developed what was called the Salter duck. And part of the development program was to build a wide tank so that they could recreate realistic sea conditions in a lab environment to see how these devices would respond and see how efficient they were. And that whole technology evolved kind of on its own, recreating sea states in the lab. So yeah. So these are waves being generated in the wide tank.
This is a deep water plunging breaker.
Yeah. There's a
It's not a
series.
wave you're ever likely to find in a reef. But it illustrates the final
Oh, it's coming through that thing, isn't it?
in synthesizing tank waves.
I'm going to shut up and comment at the
Starting
end.
phase.
These wave
This
bands,
wave requires precise control.
they don't just generate
as many
waves,
of
they
the
also
algorithms
absorb
wave
energy.
chains,
So any
but
reflections
also
coming
their
back will be
phases
absorbed by the
at
wave
startup.
makers.
The frequencies of the
Changing the
control
phase
are
allows you to bring waves
and
together
their
at some
angles
point in
have been
space, and that's how
chosen
they're
to
generating
focus.
this deep water plunging breaker.
But only by precisely controlling their relative phases can the crests all be made to coincide at the same position.
The other thing is, I mean, here you have a glass section, which means you can see right inside the internal parts of the wave, and that means they're much easier to study using a variety of different optical
We can
techniques.
repeatedly simulate the most extreme ocean waves.
Yeah, I need to stop that there.
Technically, this is a deep water plunging breaker.
The bit I wanted you to see was the long wave channel, and this is where dispersion comes into the equation. The wave pattern was going back and forward very rapidly to start with, sending out the short wavelengths that are moving much more slowly. And then it slows down and it brings in these longer wavelengths, and they all catch up on each other in the glass section that's used to study the wave. So we're using dispersions that mean of building a steeper wave than we would normally be able to within a short environment.
But only by precisely controlling their relative phases can the crests all be made to coincide at the same position. But it's in realistic sea spectra that phase control is most important.
Yeah. See that? So it starts off sending out the little ones and follows it up with a long wavelength. And then this is now the current generation white tank. It's no longer square, it's circular, and it has wave makers all the way around it. So you can generate within that circular domain sea states that are almost unlimited. In fact, so much so that you can generate states that, that are not even ever going to happen in the sea. So this is so this is done by taking different components, sending them out and having them all combined. And then they do a dual spout. See how things just don't look that exceptional until it appears. And this is the essence of this freak wave, where things can be looking relatively, maybe a bit choppy, but when things combine constructively in one location in space and time, it can produce some amazingly spectacular results. So
Does this
here,
happen in nature?
4.
Does this happen in nature? A force out like that?
No. I mean, when you have 2, the probability of that happening is infinitesimally small. A single spout does happen. I mean, that happens, and it's speculated that actually happens more frequently than was first anticipated. Certainly, statistical calculations or mathematical modelling hadn't anticipated the frequency with which freak waves actually seem to occur. And I think satellite imaging has shown that they occur on a relatively regular basis. So the last thing I wanted just briefly to mention was that all of this work, modelling things inside and understanding what these spectra gleaned from the sea mean, is that you can model things in a lab and you can refine tools like this that are used to extract energy from the waves. This long red thing at the back was developed, it's called Callum, and this was developed by one of Steve Salter's students, Richard Yen. He started a multi-million pound company, and they've actually had these out in the sea and have generated electricity from them. This is called Limpet, and there's I think 2 or 3 of these on the coast of Scotland, and of course 2 other kinds of wave devices. One of the biggest problems with these wave devices is not getting them to extract energy from the sea. That's relatively easy. What's difficult is getting them to the point where they can actually sustain extreme seas and not be destroyed by them. That's where Calamus comes in. It's a huge structure, and it can be locked down or even sunk underneath the water, where the amplitude of the wave oscillations are much lower. So that's all I have, and I'd be happy to take any questions.
Questions I wanted to say really quick. We really want to thank Nancy Salisbury and Rutabaga for letting us have these technical talks here. It's a real treat for us to be able to present technical subjects to paddlers. If that's something that you value too, please go to the website for Canoecopia and register your feedback.
Thank you. Thank you.